Hey there, this is Barry Shans, founder of Mobile Audio Academy, and here we are to talk about a very common obstacle for people, mainly who are dealing with a programmable DSP. Question is, how would a perfect bandpass look on a DSP? And to get into this, we're going to look at who is Ramondo, what did he build, what did he do to contact me to look for help? Specifically, what did he want my help to solve? And then we will be discussing my crossover curving process for setting crossovers. It's a 3-part, 6-step process that you can use. We will review Ramondo's Helix DSP settings. He shared his preset file with me. We will be reviewing my recommendations, and of course we'll talk about how I came up with these recommendations. We need to talk about a topic of speaker behavior, performance, dispersion, and we'll talk about how that directly relates to choosing some of these crossover filters. And in this kind of a unique build that Ramondo did, we need to talk about how to build your bandpass with a combination of DSP and amplifier crossovers. Do you struggle to choose sensible crossovers on a DSP? Now, what do I mean by sensible? We're going to get into that in a few minutes. Is it overwhelming to have so many configuration options on a DSP? It's likely that it'll be yes, because in my own experiences, it's been extremely overwhelming to look at what a programmable DSP has to offer and to even figure out, where am I supposed to start with this? Who is Ramondo? Ramondo is currently National Guard active duty. He's been in that for 15 years. He's not yet close to retiring. He's a native of Chicago, currently living in Oklahoma. He is an independent distributor for PowerUs amplifiers. It's a Brazilian amplifier manufacturer. And you can find Ramondo, and I encourage you to check him out on Instagram. It's at DABASSGOD. That's DaBassGod773. What he's working on is a Chevy Tahoe SUV. The whole interior is devoted to his mobile audio system. We kind of hooked up by a Facebook audio group, and he reached out to me by Messenger to ask about, should I get rid of this DSP that I already own and get a Helix DSP? So I kind of guided him with that decision. He picked up the Helix DSP.3. And then sometime later, he sent me another message. How would a perfect bandpass look like on a DSP? And that question, I didn't have an answer for him right away. We'll discover a little bit later on in the video. That's a really difficult thing to answer, and I think I got a pretty good response for him. I want to know what you think, though. So moving on, let's talk about crossover curving. It's a 3-part process, and the beginning of this is called look and evaluate. We need to determine where and how do I get to control the crossovers, and then which settings matter the most for my unique system configuration. The second part is pick and set. So what that means is pick the crossovers, what type of crossover, what slope, what frequency for the turnover, and then, of course, set the crossovers. And then part 3 is test and commit. Of course, in any kind of a system that you're building, you need to test it. And then you commit to it, which means I want you to stick with the settings that work. You've determined by testing that they work acceptably well. And then you don't play around with the DSP or tweak it or change the crossovers because you have some idea that you want to try. You commit to it and then you leave it alone and enjoy the system. So let's get into this. Look and evaluate. We need to answer questions. Number 1, what's the audio equipment? What are we dealing with? Number 2, what's the signal path? Let's go down the list here really quickly. Let me go through this list to give you an association between the type of the speaker and where Ramondo physically located them in the vehicle. He's got the tweeters in the A-pillars, the front doors, and the center console. There are 6.5-inch midwoofers in the kick panels. We've got the 8-inch woofers located in the front doors. The 10-inch mid-bass woofers are in the center console. Kind of the only logical place to put all these subwoofers is in the back half of the vehicle. Now we're going to take a look at a system layout diagram that I created. The project name is Project Power Us. The objective is a loud and clear musical demo for the US crowds. Remember, we're dealing with Brazilian amplifiers and speakers. So what we have going on at the top is the Pioneer head unit and the Helix DSP. We have the SCAR amplifiers powering the tweeters. We've got a PW1600 amplifier powering the 6.5-inch woofers. We have a PW1600 amplifier powering the 10-inch mid-bass woofers. We have 4 of the PW13500 amplifiers. One amplifier goes to 2 subwoofers. And lastly, we have the PW3500 amplifiers. One amplifier handles 4 of the 8s. Now, the next part of this is a signal path diagram. This is something that I would encourage any of you to draw for your own system. And the purpose of this is to understand the flow of the signal beginning at the input, which is the head unit. And if you have a DSP, that's inserted in the signal path as well. And then it's going to be branching off, divided by the DSP into the different amplifiers. So each one of these, we have amplifiers, and over here as well, amplifiers. Now, just to contrast this with a more simple system, we've got a 3-way active system where, again, we have the head unit to a DSP, 2 amplifiers, we've got the one amplifier for a subwoofer and a 4-channel amplifier going to the tweeters and your mid-bass woofers. And something available for you if you wanted to download this and fill it in on your own. It's a 3-way active crossover planner. Put in the most common types of filters that you would need to use, beginning with subsonic, which is your high-pass filter for the bass, low-pass filter for the subwoofer, high-pass filter and low-pass filter for the mid-bass, and then lastly, your high-pass filter for the tweeters. And for Ramondo system, I made a simplified signal path view that has the actual output configuration that he will need to use, because what he really has is a 5-way active system. We're not using any passive crossovers, and he's got these 4 different sizes of speakers that all need to have their own bandwidth, their own bandpass. And then, of course, the subwoofer needs to have its own filters separately. So that's how I came up with the 5-way designation. And then what specifically is going on here in this highlighted section is 2 channels of output from the DSP going into RCA Y splitters, so we can double up these outputs. And then what we have going on is the mid-range is split to these 2 amplifiers. So we have to do a bandpass using DSP filters as well as amplifier filters, and that's going to be for the 6.5 and the 8-inch woofers. Okay, now we need to look at the DSP software so we can begin to really dig into the meat and potatoes of this lesson. What we have going from the top down in this section is the channel output assignments. We move down to the high pass filters, low pass filters, phase polarity and time, channel gain, and output level controls. In the middle is once you set up some of the crossovers, you're going to get these colored graphs, and these correspond with the outputs. And down at the bottom we have our equalizer controls. This lesson has really nothing at all to do with equalization, so just know that it's here. And we're going to come up to the top right and select I/O. Now we have a different window entirely. This is input and output configuration. On the left upper right side, we have the main inputs. This is how we're going to deal with the RCA outputs from the head unit. We're basically telling the software what is coming in. What's going on the left, lower left corner of the input section is some inputs that Ramondo does not need. And then the output assignment, it's like it says, it's a drag and drop interface. So what's going on here is we take one of the inputs, front left, and we drop it over here front left going to front left high output. If you think about this a different way, it's kind of replacing what you'd be doing with a bunch of RCA patch cables, except this does it all within the software. While the Helix crossover setup allows several different types of crossovers, there is one that I'm going to be using across the board, and that is Linkwitz-Riley. So what we have is a simulation of the electrical response using the LR4, which means Linkwitz-Riley fourth order. That's negative 24 dB per octave. And then this nice flat kind of bridging over these two curves. That's the type of transition we want to encourage to happen. This, again, is a simulation. There are lots of different reasons why this perfect flat response here is not going to actually happen in the vehicle. But the point is to have predictability and to eliminate a lot of these other crossover options that are, frankly, they're not all necessary. When it comes to addressing the crossovers between the top end of the subwoofer and the bottom end of the 10-inch mid-bass woofers, we're acting on the assumption that we want the bass to be quite a bit louder than the rest of the system response. So what I have chosen here is a 55 hertz low pass filter for the subwoofer channels, a 75 hertz high pass filter for the mid bass. Now, there are additional reasons for choosing those frequencies. Ramondo informed me that he is expecting the subwoofers to not give much output above 55 hertz. And logically, we can assume that giving a higher crossover frequency is not going to encourage the subwoofers to play higher, because it's not likely that it's going to happen. Now, the mid-bass high-pass filter, it actually falls right in line with the resonant frequency of those drivers. And since this crossover alignment is 6 dB down at the crossing frequency, a lot of power is already being cut from the amplifiers at 75 hertz. So we're trying to get this nice smooth transition happening so you get really nice mid bass. I will walk you through my recommendations for Ramondo to change his Helix crossover settings. What I'm going to do is start at the low end, work through the mid-range, and then end at the treble. So we're starting with subwoofer 1. The high pass, this is going to function as the infrasonic or the subsonic filter. So we are going to go with 20 hertz as our crossing frequency, Linkwitz-Riley crossover characteristic, 12 dB per octave slope, the low pass filter, that is to cut off the top end of the subwoofers. We're cutting at 55 hertz, Linkwitz-Riley, and fourth order, or negative 24 dB per octave. What we have next is the crossovers, the bandpass for the 10-inch mid-bass woofers. We're doing a high-pass filter, 75 Hertz. Again, Linkwitz-Riley 4th order. Low-pass filter, we're doing 200 Hertz. Same as before, Linkwitz-Riley 4th order. And I wanted to comment on why is it such a narrow bandwidth. I mean, 75, this isn't even 2 octaves, but since we're doing a 5-way system, we have to cut this up into some smaller slices than we would with, say, a 3-way or even a 4-way system. Now, the mid-range, this is actually going to have to be split up with the RCA-Y cables after the DSP. And that's why we're going from suddenly like that 75 Hertz to 200 Hertz, that little tiny bandpass, to 200 Hertz all the way up to 8 kilohertz. And something to note here, the low-pass filter of 8 kilohertz is Linkwitz-Riley 12 dB per octave. I'm not going with that 4th order slope here because this is actually used kind of like a secondary crossover just to ensure that some of the possible cone breakup distortion is going to get filtered out. Now, this is going to be actually a low pass happening at a lower frequency using crossovers built into the amplifiers. And so, just to state this a different way for clarification, this is what I mean about using a combination of DSP filters and amplifier filters to build the bandpass. So I can't show this to you all in one picture here, but that's what the overall end result is going to be for the mid-range. That will be, again, the 6.5-inch woofers and the 8-inch woofers. And this one is 3 kilohertz, negative 12 dB per octave. So the question here naturally would be, why would I not do a 4th order crossover? I'll get into that in a moment. There's something else really important we have to talk about before I can wrap this up, because we have to choose our low-pass filter crossover frequency for the 8s and the 6.5s. Now, I don't want you just to be guessing at this, because frankly, that's the easier way to do this, and you might already know intuitively this is how I want to do it. But I'm going to go at this from a scientific modeling kind of approach. And we have to introduce this colorful chart here on screen. And let's focus on these hemispherical diagrams here with these like narrowing sections in the middle. It's part of a polar response graph. You can do this for loudspeakers, and if you're familiar with microphones, we do it the same way, except those tend to be like a full circle kind of polar response. But anyway, if we have just pick the 6-inch woofer diameter and focus on the orange column, that's going to be essentially the highest like theoretical low pass filter frequency that we'd ever want to choose. Once you get into this red column, the dispersion is extremely narrow, and there's kind of a common analogy here, which would be the wide dispersion is like having a flood lamp, like those security lamps that like you might have on the outside of your garage door or at the door of your house. And then the really narrow dispersion is like a spotlight, or like if you have a nice flashlight where you can kind of rotate the end of the lens and make that beam really small. That's where the speaker beaming concept is often explained. So we can use this to determine like an ideal top end of a 6-inch woofer. Now, I can't have Ramondo running his speakers crossed like this. And the reason for that is we also have to match this up with the bottom end of the tweeter. I don't want you running a 1-inch tweeter like these massive audio tweeters. Don't run those at 2260 hertz, because it's very likely, even if we could do a very steep crossover slope, once you listen to the system loudly for a long time, like we all want to do, those tweeters are going to, at minimum, sound very strained and distorted. And it's very, very likely that those voice coils, which are extremely short and don't have a lot of mass to it, those voice coils are going to melt. And you know what that means. So we have to do a compromise here, which means we move that low pass filter for the 6.5s up to a higher frequency. The compromise is a little bit more narrowing to the dispersion. And so that's what I was thinking when I came up with that 3000 hertz crossing point. Now we have to wonder, why would you even be thinking about dispersion anyway? Why would it matter so much? So the concept here is to spread the sound out as widely as possible in as many speakers as we can. So one way to think about that is, if you have more speakers to divide up the audio spectrum, it's more likely that you're going to have all these speakers in a very wide dispersion. So why doesn't everybody build a 5-way system if that's so potentially beneficial for sound quality? Well, it's better to try to keep it simple. The more speakers, the more active channels you add into the system, the harder it is to do the wiring properly. You have more amplifiers you have to fit in the vehicle. I could tell you from experience, it gets to be just quite a handful. And if you're paying somebody to do that kind of an installation for you, well, that equates to more labor. You're paying for more labor than you might need to get your system response goals met. Where if you did it with fewer speakers and maybe you spent more money on high quality speakers, you could get outstanding results with a more simple system. I want to show you yet another way to think about this system. We've got acoustic crossover targets. So far, almost everything I've been discussing is about electrical crossover behavior. We've got another thing just to muddy the waters a tad here, but it's really important that I at least introduce it before I end this video. So we have an acoustic crossover target of 65 Hertz. That's right in this region for the top end of the subwoofer and the bottom end of the tens. The next acoustic crossover frequency is coming in at 200 Hertz. That is the top of the tens and the bottom end of both the 8s and the 6.5s. The next crossover frequency is, this one actually is not an acoustic crossover target. And the reason for that is because we have this entire section of 200 Hertz to 3 kilohertz. That's going to get where the 8s and the 6.5s have some overlap going on. Overlap is how we cause an acoustic crossover to not happen. So this is a compromise. Normally I would not set up a system to intentionally have this overlap, but it's something that we have to deal with as a limitation. So then the final acoustic crossover target is 3 kilohertz, which would be, we're encouraging that to happen with the top end of the 6.5s and the bottom end of the tweeters.